very much for being here. It was a bit difficult to organize this one specifically. So thank you very much to René for accepting late notice to come here. And he will tell us everything about there is to know about the AMOC, the current work on the AMOC collapse and the rapid climate change is also a novelty. So thank you very much. The floor is yours.
Thank you so much. So my name is René van Westen. So I received this message from Meridional last week, and he started like, please say yes. So that was like, okay, I need to present something, and then he asked whether I could come and step in for Henk Dijkstra. So he was intended to give a talk, right? Yes, but I'm very happy to also give like an overview of what we have done in the past couple of years, like work on the AMOC at the tipping point and trying to understand how it tips and how it cracks. So that's what I'm going to explain in the next 40 minutes. And I think that maybe is everybody is familiar with tipping elements or tipping points or whatsoever, right? That's the background of the tipping series. So that's great to hear. But for this talk in specific, we're going to talk about the Atlantic Meridional overturning circulation. So Atlantic stands for the Atlantic. Meridional means a circulation in the south-north direction. Overturning is the circulation that has a synchronous motion into the deep sea, and circulation is that it keeps itself driven by all different kind of feedbacks. So here you can see a schematic of the ocean circulation system. So the red arrows indicate usually surface currents, and the bluish colors indicate currents that are at greater depth. And you can nicely see that all the basins are connected throughout the ocean. But there is like one specific basin in particular, and that is the Atlantic Basin, for which you have, starting all the way from the south, you have a northward flowing current near the surface. It sinks around the Greenland ice sheet and then returns as a cold, deep undercurrent. And this is quite different if you compare it to the Pacific Basin or the Indian Ocean Basin. There you have mainly have a wind-driven circulation. They are specifically much weaker compared to the Atlantic ones. So this is a lot of details, but if you now make a even more simplification of the Atlantic Basin, shown here again. So again, you have these kind of surface currents, then you have sinking around Greenland, and then this cold deep undercurrent. So you have this conveyor belt picture here in the top left. So that is how we treat the Atlantic Meridional overturning circulation. And sometimes also with media communication, we refer this as the Gulf Stream, but actually it's the AMOC, and the Gulf Stream is also indicated over here. It's only a small part of this upper branch of the Atlantic Meridional overturning circulation, or AMOC for short. So this is the present day situation. It is in a very strong regime in a northward case, but it is also a tipping element, meaning that it can go transition from a strong state to a substantially weaker one, shown here now on the right. So that is something we would like to study and to understand if it is transitioning from one state to the other state. And to understand why there are two different regimes, we can look at the drivers of the AMOC. So we know that the ocean is forced from the atmosphere, from the top, and there are a few main contributors. So we have wind. But for the AMOC, wind is relatively small. I think I hear an echo. Just mute myself. Sorry for that. But for the AMOC, what is most important are density differences, which arise from temperature differences across the ocean. So, for example, near the equator, you have relatively warm water masses. Well, at the North Pole, water mass is relatively cold. And due to these higher temperatures, you're getting net evaporation near the equator. And also due to colder weather, you're getting more precipitation at the higher latitudes, and therefore you have precipitation. So these water masses are relatively fresh and cold, while they are relatively warm and saline at the equator. So we can actually look at the different kind of drivers and circulation regimes you can expect if you now are going to separate salinity and temperature from each other. So what we do is we look at the Atlantic Basin from a side view. So here you see two different boxes. So on the left, you can see the temperature-driven circulation, and on the right, the salinity-driven circulation. So what I already said, this is like a side view. So here at the top left, you are at the equator at the surface. This is the top right, the North Pole, also at the surface. And this is then at the equator at the bottom, and the same for the North Pole at the bottom. And the same case holds for the salinity one. And now we can fill in what we know from the climatology. So for the temperature case, near the equator, we have relatively warm waters sitting at the top, and near the North Pole, it's relatively cold. And you also have evaporation and precipitation, like described above in the previous slide. So you have relatively saline water sitting at the equator for the salinity case, and you have relatively fresh water sitting here at the top right. So this is the standard layout of our circulation. And now we're looking what will happen due to these density differences. So we know from the equation of state that if you heat up some air or some water masses, they are expanding, meaning that the density becomes lighter. And of course, when you cool certain density or fluids, you have usually the density becomes larger. So for the temperature case, you get relatively heavy water sitting at the surface in the North Pole, but exactly the opposite is true for the salinity case. Because more saline water means that your water masses becomes more heavy. So you see nicely this kind of symmetry breaking in these circulation regimes. And if you have relatively heavy water sitting here near the surface, you get a sinking of circulation. So this is like what we call the overturning. But of course, this water masses sink. You will get like a vacuum over here, which of course is not happening in the real ocean. So you get like a surface-driven current as well. So for the temperature case, you get like a surface current from the equatorial regions to the North Pole. But for the salinity case, you get like a surface-driven current the exact opposite way from the North Pole to the equator. And now we can fill out the entire circulation, and you get like a clockwise circulation for the temperature one. And then for the salinity case, you get the exact opposite. So those are the different kind of balances that are into play. And instead, we are, of course, not dealing with a quantum physics system in which, of course, both equilibria can coexist. We are only observing one. So that means that also one circulation must be, of course, dominant. And in the present day case, that is mainly temperature. So if you would fit those back in, squeeze everything together again, you nicely see that you get like this clockwise circulation. So the temperature differences are slightly dominant over the salinity ones, and hence we have this clockwise circulation going up. So we have cold and fresh water. So cold gives heavy water, fresh gives lighter water, but the cold one dominates, and therefore the net effect is relatively heavy. Therefore, you have the sinking in the north and the clockwise circulation. So that is like how the AMOC operates on a very basic and simple scale. And we know that the AMOC has a tipping element. Why this is the case, I will also explain it in a few slides from now. But what we know is that we have this one equilibrium, that is this temperature-driven case, so this clockwise circulation. But the AMOC, under a sort of forcing, can transition to the other equilibrium, so that is the salinity-driven case with an anti-clockwise circulation. So that these are these different equilibria that are into place. And we can test this, and this was already done like almost more than 60 years ago by Henry Stommel. So he had this very idealized two-box model, so it's tried to capture those different kind of effects. So what he actually had, so he had like this North Pole box, what I described before, and he also has the equatorial box. There is some temperature effects, but you can ignore it from now. And what he actually did within this model, he tried to increase the amount of evaporation and precipitation by this EDA. So that is our forcing, our control parameter in this in this idealized model, such that you can change the salinity difference. You can make them more important or less important. And then we can see how actually the circulation is reacting under a different value of this freshwater flux forcing. So we're mainly interested in the salinity differences and not so much by temperature in this idealized model. So here on the horizontal axis, you can see this our control parameter. So that's the freshwater flux forcing. And on the vertical axis, you can see the circulation strength. And we start from our present day situation. So that's the strong northward overturning regime, which I've indicated here as a black curve. So that is our AMOC on state that we know is present day situation. And if you increase this eta parameter, you're actually effectively are then adding fresh water to the northern box. You're getting a more saline equatorial box, so the salinity difference that becomes larger and larger, and this causes the circulation to weaken. So you have less sinking in the north, but you still have quite a large range of AMOC regimes. Then eventually, you can increase that until your settlement verification, so your tipping point in the system. So this is the last stable AMOC state. And if you then add a very small perturbation to the system, then the circulation fully collapses to a completely weakened and reversed state in the system. And then if we are at this state, we can of course reverse the forcing again. And now you see you follow a different kind of path. So you have this very nice hysteresis diagram. And again, also for the off state, there's also a settlement verification. And eventually also your system does recover to the AMOC state. And for this simple model, we can actually calculate all the different kind of steady states. And we also have the unstable branches here. But what is the most important thing is that we have a clear multi-stable regime with this very idealized model.
Yes. Does the left one also cerebral fiber? Yes.
Yeah.
Although it's not really parabolic.
No, yeah, exactly that. So we have different kind of regimes, and of course you can indicate that with these arrows. So that is something we found with this idealized stall model. And of course, you can criticize that because it's a very simplistic way of our ocean circulation, but it is very nice that you get these kind of simple behavior with such a simple model. But why does this settlement verification exist in the first place? That means that there is some kind of feedback mechanism that comes into play. And for the case for the AMOC, it is the so-called salt advection feedback. And I try to explain as follows because it's very important, and it will come back also further down the line. So this was again this idealized circulation that I sketched before. And what we have actually done with our control experiment is that we were adding fresh water to the North Atlantic Ocean. So which I've indicated over here with a precipitation plus, so a positive anomaly in your precipitation, meaning that you have more fresh water in the northern box, so in the North Pole region. So this becomes slightly more fresh due to our imposed anomaly, and that means that your relatively heavy water masses become less heavy, which I've indicated here with the minus sign. So this is our initial perturbation, and let's see how our circulation starts to react under this freshwater perturbation. So what happens is that if this becomes lighter, you have less sinking, which means that the whole circulation needs to weaken as such. So under a freshwater perturbation, you always expect that your AMOC is slightly getting weaker. But now this salt advection feedback kicks in. And the main thing is that this surface current is transporting relatively warm, but also relatively saline water towards the north. So that means if this strength of the surface current is weakening, you're also transporting less salinity to the north, meaning that our initial perturbation can amplify itself. You're simply receiving less saline water, so this becomes even fresher, therefore this becomes even lighter, therefore you have less sinking, and therefore the circulation reduces even further. So this is the runaway feedback loop in the system, the destabilizing salt advection feedback, and that causes the AMOC to transition from one state to its current state, the present day state, to a fully collapsed or reversed state. And this is something that has been shown in the complete model hierarchy that is available. So here you can see a 20-year-old paper. So these are all different kind of models. So what they've done, they added the same kind of model experiment, like the standard model that I showed before, with these two different boxes. So they have much more complexes. So they also have like an ocean, they have some sea ice and idealized atmosphere. And they also increased the freshwater flux forcing. They found an AMOC collapse, then reversed the one to show and demonstrate this hysteresis behavior with a more sophisticated model. But these models are also highly idealized. This has been shown by, I think, Dijkstra as well, with a fully global ocean model in which you can also calculate all the different kind of steady states. So again, you have like an AMOC on and an AMOC off regime. This is again for a more sophisticated model, again, including more processes from the famous model. So again, you start from here, you add some freshwater fluxing, get an AMOC collapse, then reverse it again, and then eventually AMOC recovers. So again, demonstrating hysteresis behavior. This was with one of the previous generation of climate models, again demonstrating hysteresis behavior. But however, this kind of hysteresis behavior for the AMOC was still missing in the most recent climate models. So they found different kind of AMOC regimes. So here you have the AMOC strength. So this is like a control simulation. Here you see an AMOC collapse, but they added tons of fresh water instantly. So they took like the entire Greenland ice sheet and dumped this all at once into your Atlantic Ocean. That is one very effective way to kill your AMOC, but then you're simply, not seeing any of the feedback or the destabilizing feedback mechanisms anymore. So therefore, it's very hard to say, like, is this now like a forcing induced or like a true salt advection feedback case? So like a feedback induced tipping event. There are indeed some indications, but within the AMOC community, there was a lot of debate whether this salt advection feedback also comes into play if you go to the more sophisticated model. So that was still missing. And we, or mainly Dijkstra, but I also thought about that. Can we now show this also using these most modern climate models, which include all the different kind of processes, to find that this salt advection feedback also plays a role in the most recent climate models. So what we have done is we took such a model. So we have a 1 degree ocean resolution, a 2 degree atmospheric resolution. So that is like a very typical horizontal resolution for the latest climate model configurations. We also have sea ice and a land component as well. They have similar kind of resolutions. And what we have done, we were adding some fresh water into the North Atlantic Basin over here, over this region, and we compensated elsewhere to conserve total salinity, which is shown here as indicating this mask. So what you see over here on the horizontal axis is a freshwater input, and on the vertical axis is again the AMOC strength, which is measured in swirldrops, not in sievert, so it's not radioactive. So I'm not sure. So this is like 1 million cubic meters of water per second. So it's about a mean strength of 17 swirldrops. And to give you like some impression, if you take like all the river output from all the rivers, that equals about 1 swirldrop. So this whole circulation system is like 17 times all the combined rivers. So that's quite a lot of water that is just flowing around. So we start from that present day and observed state, and we are adding fresh water. So we're effectively repeating the same kind of experiment what Stommel did already in 1960. So if you do so, you see under increasing freshwater flux forcing, our circulation is weakening a little bit, not that much. There's also a lot of variability on top of that. This is due to atmospheric, ocean, and sea ice feedbacks, just the climate feedbacks that play in a role. So you get a lot of interannual variability. But overall, you can see that the mean state is gradually weakening. And then eventually it is weakening even further. But now we are at a crucial point that we are now at a tipping point, and eventually your AMOC does collapse to a completely collapsed state as well. And then again, we reverse the circulation to find some indications whether there is some clear hysteresis behavior as well. So now following to the left in the red curve, you stay in this off regime, and eventually your AMOC does become slightly stronger, but remains in a completely weakened state, and eventually does recover. And then eventually it will equilibrate further, but we have not continued those simulations as well. So that was very nice that we could demonstrate that. And it was also very neat, if you have such a climate model, you can also look, for example, at some of those impacts, at the transient responses that also come into play. So this collapse takes about 100 years, which looks very long, but on typical climate timescales, 100 years is very abrupt. And then we can actually see how the climate looks like. So what's good to keep in mind is that we only vary here the amount of freshwater input, but we keep climate change levels to the pre-industrial ones. So we didn't consider any of the climate change effects as well, which we will discuss further. But then we can look, for example, at the temperature impacts in such a climate model. So what I show over here is the temperature difference in the annual mean temperatures. And what you see, if the AMOC shuts down, you get like cooling over your northern hemisphere and warming over your southern hemisphere. And why is this? Why do you see this clear seesaw pattern between the two hemispheres? Well, the AMOC is effectively taking heat from the southern hemisphere and dumps this in the northern hemisphere. And if you shut this down, all this heat will stay in the global south, and the northern and the global north will cool. In some regions, such as Norway, they can see a drop of 20 degrees Celsius in their annual mean between the two different states. So that is a very big temperature shift. Also for the Netherlands, it's about 10 degrees Celsius. So quite some dramatic cooling. Precipitation, you will also get less precipitation over Europe. Here you see also some brown colors, so it means less precipitation. The green colors indicate more precipitation. And what you see over here is that the tropical rain belts, they shift actually southward under the collapsed AMOC. And over the Amazon rainforest, we actually found that the dry season became the wet season and the wet season became the dry season. So completely different seasonality over there. The AMOC is also important for shaping your regional sea level. So if it collapses, you get additional sea level rise, up to 50 centimeters in the North Sea. And my personal favorite, but maybe also the most worrying one. So this is the Arctic sea ice extent before the collapsed AMOC. And if the AMOC collapses, sea ice extends all the way down to South England. And even our North Sea is covered under sea ice. There's some very spectacular differences in our present day climate, really shifting to a more continental climate. So that is something nice, but can we try now to understand why the AMOC also collapses, and can we a little bit go into the dynamics of this collapse? So to quantify this strength of the salt advection feedback, we can measure how much the AMOC carries the amount of fresh water going into the Atlantic Ocean at 34 south. So actually it's a conveyor belt, so what must come in must come out. So we can actually measure at 34 south the AMOC because it's flowing northward near the surface, and at greater depth it's flowing southward. So we can just measure those properties at 34 south and see how, of course, things differ along the way, but that can actually tell you something about the strength of the salt advection. And what we do know, if this quantity is negative, that means that this AMOC is in this destabilized regime, so the salt advection feedback is active. It is maybe not dominant yet, but it is at least active, so it's trying to destabilize the AMOC. But when this quantity is positive, actually it is stabilizing the AMOC. And what we know from theory is that what you are expecting for the AMOC onk is that you're in this regime over here. And what you nicely see is that this FOVS value, if it's in this negative regime, you will first get a minima, and then you will reach the tipping point, and then you go to this AMOC off regime. So that is something we know from theory, is that if you are approaching the tipping point, you will go through a minimum in your FOVS. And your FOVS is always negative prior to the AMOC tipping point. It also holds for the standard model and for the other climate models as well. And if you then look, for example, at most climate models, if you look at this indicator, so here there are a lot of crosses and marks, but here on the horizontal axis, you can see this FOVS parameter. On the vertical axis, you can see your AMOC strength. So this cyan colored curve here is what observations indicate. It should be negative. And actually, if you look at all climate models and you just add them, most of them have a positive FOVS bias, which means that they are simply underestimating the strength of the salt advection feedback. So meaning that the AMOC is not sensitive enough, and that also implies that they underestimate the risk of tipping. And that is also something we have in our climate model. So what you see here now is this FOVS parameter. So we start from a very positive value. So that means that our AMOC is way too stable. So we add, first of all, a lot of fresh water to get this negative. And then what you nicely see, we're going through a minimum as well. And this happens prior to the tipping event. So that nicely aligns with theory. And also the variance is increasing when approaching a tipping point, which also means that your AMOC is getting more and more unstable. So this nicely connects what we saw with previous results, but now with a more sophisticated climate. And what we concluded also back in this 2024 study is that we looked at all the available observations and reanalysis data. So going from this model output, we know that a negative trend means that you're getting to a more unstable AMOC. And what we found for most reanalysis products, although they have a negative FOVS, this is for model years, or actually calendar years, there is a slightly negative trend among reanalysis. So we were concluding, hey, the AMOC is going into the direction of the tipping point. So that is something what we also mentioned in that major study. So that was a big thing, and we had a lot of headlines on the international media. But then we ran into some problems, and one of the problems is that this whole indicator only works under equilibrium or quasi-equilibrium conditions. So that means that if you do this hosing at a very slow pace, what we have done, then this all works. It nicely connects with theory. It nicely connects with all the way to the stomach model. But as soon as you, for example, impose climate change, this whole thing breaks down. So therefore, we need to do some things. And therefore, we came up with some new additional experiments. So what we first did is with this whole hysteresis simulation, we always had a varying Hosing parameter in the background. And we didn't apply any climate change. So we now try to do the opposite ones. So we fix the Hosing values and then trying to alter the Hosing space. So instead of going into like a 2D direction of your verification space, we also add like another layer here in the third dimension in which you also vary climate change as well. So what we did at different points, we branched the simulation, but then keeping the freshwater flux forcing fixed. So we've done that at 4 different points. And eventually we are in a stable state. So we get different kind of steady state. So for a higher freshwater flux forcing, but also for a lower freshwater flux forcing. And what is most important is that we branch from those equilibrium points, we branch our simulations under climate change, but keeping a constant freshwater flux forcing in the background. We know that this freshwater flux forcing is not ideal. It's like some kind of bias correction to get like a unstable AMOC. So meaning that this salt advection feedback is activated, but it is not dominant yet. But for the other one, for the 0.81, the AMOC is in a very stable regime, so you're expecting less or no tipping at all. So from those different kind of equilibria, we initiated different kind of climate change simulations. So here on the lower left, you can see the lower left. On the left, you can see the lower freshwater flux forcing case, so the ones with a stable AMOC, and here on the right with a higher freshwater flux forcing with a more unstable AMOC. So we first started from the historical simulations, so from the historical emissions. So you see hardly any differences. And then we have the climate projections until 2100. And what you nicely see, so this is like the blue curves here are now in an intermediate scenario for which the climate warms by about 2 degrees Celsius by 2100. And what is nice that for both cases, you see that the AMOC is going down, it's weakening. And then we continue the simulations even further to see what the future fate is of the AMOC. And what you nicely see is that for this case, indeed, the AMOC is collapsing under the intermediate scenario because the AMOC is more unstable. So it really reduces to 0. But for the one on the left, actually the AMOC is weakening temporarily. It stays there in a weaker state for about 100 years, but eventually does recover. So this is very nice to demonstrate that. If you add like a business as usual scenario or like a Trump scenario, some people call that. So with a very high emission scenario, what you nicely see is that That's the red curve, so you have like 5 degrees warming by 2100. You can see that the AMOC collapses for both cases. So therefore, this is important. It stresses that cutting our emissions really helps to reduce the risk of AMOC tipping as well under climate change. But if we then look at this FOVS parameter again, so this instability, the instability measure. So here again for the right, we starting from negative values. So therefore the AMOC collapses in both cases, which makes sense because we are in this unstable regime. But for the left one, we are in this positive regime. So you're not expecting an AMOC tipping event to take place, but it does actually for this red curve. So for the 8.5 scenario. So the AMOC does collapse, which means that you can still trigger this salt advection feedback despite being in the wrong regime. So how does that work? So then we have a different kind of perturbation to start with. So again, the destabilize salt advection feedback, but now under climate change, so that's very important. So if you add climate change, you're not affecting precipitation that much, what we did with the hosing experiments, but what you're now affecting is mainly the temperatures here sitting in the north. So what we're actually doing is we are heating up the Earth quite a lot. So that means that the North Pole region is getting less cold, which I've indicated with the minus sign. And that means, again, that these water masses are getting relatively light. So effectively, this is getting warmer, meaning expansion, lower densities. So this becomes lighter, you have less sinking, and of course, the whole circulation is reducing in strength. And then again, you're getting less salinity transported to the north, and this becomes fresher, becomes even lighter, you have even less sinking, and again, this salt advection feedback is triggered. So a slightly different setup, but with a similar outcome if the forcing in terms of climate change is strong. And therefore, you can still, with a positive FOVS, you can still have a collapsing AMOC, but you probably need to add more climate change forcing to trigger that one as well. So climate change induces AMOC weakening, but if this weak AMOC is strong enough, you get this destabilizing salt feedback despite being in this wrong regime. And what we also did in the paper is that we actually tried to come up with a new physics-based indicator. I'm not going to explain it in detail, but this is like an indicator that can also measure the amount of sinking that takes place in the north. And if this black curve goes through 0, that one also works under climate change instead of this FOVS. So we also try to figure it out as well to work around that. It works very nice also for other climate models as well. So that's also something we've done in this paper from last August. So what's now the evidence is that if you now look at a whole ensemble of climate models, what we always find is that, or what we always find, in a few cases for which model output is available. So here on the horizontal axis, you can see time running. On the vertical axis, again, AMOC strength. If you continue those simulations, you see that most of them show a collapsing AMOC. So that's very nice. So that there is some kind of like consistent results among the model hierarchy from the most recent state-of-the-art climate models. And here is also what I highlighted again, this AMOC strength and time on the horizontal axis, the vertical axis. And this model was specifically simulated under a low emission scenario, so that is in agreement with Paris. So that is like staying below 2 degrees warming, but even for this model, the AMOC does collapse under this very low emission scenario. And that's very bad news, of course, for humanity if such a scenario unfolds in the nearby future. And using this new indicator that we developed, we could also estimate the risk of tipping before 2100. So in the previous IPCC report, the risk of AMOC tipping was assessed to be less than 10%. And we now find about 57% under an intermediate scenario, that's about 3 degrees warming with 2100, and almost 90% under a very high emission scenario, so that is 5 degrees warming. And we reached the tipping threshold around 2.5 degrees warming. And currently we are at 1.5 degrees warming, so we have only 1 degree more before we will reach this AMOC tipping threshold to be exceeded. And there's also the model years we've indicated using this indicator. So that's nice, we thought, because there is a very lively debate within the AMOC tipping community, whether now the AMOC is tipping or collapsing or whatsoever. So I can nicely try to explain this a little bit more, what's going on now with this tipping community and why there is a lot of controversy about this whole topic. But we can maybe start from some consensus that we have. So what we know from all the results that are available is that we know that the AMOC is a tipping element, and then specific under inclusion for flux forcing that was already shown by Stommel and by all the other models that followed. We always find a collapsing AMOC when you add freshwater to the North Atlantic Ocean. That's one thing. And what we also do know is, oh, by the way, this plot shows like all the different kind of tipping elements that exist in the Earth system. So the AMOC is one part, but you also have the West Antarctic ice sheet, the Greenland ice sheet, the Amazon rainforest. A lot of tipping elements that may be triggered on the climate change. And the second thing, what most scientists agree on, is that if you add climate change, you will get AMOC weakening, and that's shown by all different kind of climate models. So here you can see different kind of scenarios. So this is the lowest emission scenario to the highest emission scenario. Here on the vertical axis, you can see the decline of AMOC strength over the 21st century. So it starts from 0 going to negative. So that means that all climate models show weakening under climate change. So that is like where there's a lot of consensus with respect to these kind of big discussions within the AMOC. If you now look, for example, at direct observations of the AMOC strength measured along the rapid array, so these are now calendar years, and this is now again the AMOC strength. There is a lot of variability. So this blue colors indicate 12 hourly measurements. The black curve here is now the yearly average one. And there is a very slight negative trend, about 5% weakening in a decade. However, and there is a lot of debate among this. If you ask the modelers, they say, hey, the AMOC is already weakening due to climate change. But if you ask the observational, they say like, well, we don't know for sure. This can be part of natural variability. Or some other aspects as well. And also this trend is not significant, so that remains inconclusive for now. Then people try to extend this kind of time series because it's relatively short, it's only 20 years. So they tried reconstructions. And one of the most famous reconstructions is the so-called warming hole that shows up. So all the places on Earth are warming, except one peculiar spot here south of Greenland. This is actually cooling. And this is due to a weakening AMOC, so you get a very clear fingerprint. So people try to actually derive the AMOC strength based on these negative anomalies. And they concluded that the AMOC has weakening by 15% since 1950. However, you can get these kind of similar patterns by aerosol forcing or wind forcing. So that's also debated within the AMOC community. Then we have, of course, the risk of AMOC tipping before 2100. Well, I already mentioned IPCC really assessed that it's very low. Well, and now there are a few studies out, they say it's way higher. So it's more than 10%. And lastly, yes, the AMOC can tip, but there are also plenty of simulations that they add some climate change forcing, in this case 4 times CO2, so that's like imposing 4 to 5 degrees warming. The AMOC does weaken over time, but then eventually recovers. So we do have AMOC collapses, but we also don't. How do they match up? So there's a lot of debate ongoing. So who's right, who's wrong? And in the end, everybody's right. But we, of course, need to nuance that a little bit. So what's going on with climate change? Because things become a little bit more difficult. So we go all the way back to the Stommel model again and try to understand what climate change actually does with this kind of barification diagram. So this is the standard case, so this is our reference one. And I didn't show you, but there is also this landscape is also shaped by the temperature differences across the boxes. And if you add climate change on top of that, what actually is happening is that this whole diagram shifts to the left. So your settlement barification shows just lower freshwater flux forcing values. So that means that if you are sitting over here, you add a climate change anomaly, that means that you simply have no AMOC on state, so that means that you always go to this collapse one. But for the other one, you can still go to yeah, you're reducing strength, but you still go to an AMOC state. So in this case, we have barification induced tipping for the one with a higher freshwater flux forcing. And that is also something we saw. So we had these kind of two experiments for 0.8 and 0.45. So when you add a climate change anomaly for this one, the AMOC does recover. It is getting weaker, but then recovers eventually. But for the with a higher freshwater flux forcing, it does collapse. So that was a very nice interpretation of these results. So your sunlight verification shifts the lower freshwater flux forcing and means that your AMOC simply collapses. So that was nice. And then we thought, okay, let's now do an experiment to find the critical temperature level for which the AMOC collapses. Like a similar case of ramping up freshwater flux forcing in a gradual way, we do the same thing, but now for sheet. To really reassess what the critical level is for tipping for the So first, what we did is look at those simulations. We started from this higher freshwater flux forcing because that one was very close to the tipping point. We already had two cases for which the AMOC collapses. So under an intermediate scenario and under a high emission scenario. So we first did a low emission scenario. So it's green curve. So it stays below 2 degrees warming. And there you can nicely see that the AMOC remains in a strong state. So hooray. So that is one thing. So we now have like some kind of range where we need to look at. So we're expecting an AMOC tipping event to take place around 2.2 to 2.8 degrees warming. So that should be doable. And of course, we also have this kind of results, but I'm going to skip that. I'm also going to skip that as well. So what we did is we increased the CO2 concentration at a very slow pace. So about half ppm per year. So that's about a factor of 7 lower than present day rates. And this is only CO2. We also have methane. So our climate change forcing is about 10 times slower what we see with present day situations. And what we did, so we increased that. So this is now model years. And this is now the temperature anomaly. And you can nicely see we start from a temperature anomaly to 0, and we increase that up to 5.5 degrees warming. So that is way above these previous thresholds. Okay, now we'll see where the AMOC collapses. It does. There's no AMOC collapse. So here you're getting to see the model years, and now AMOC strength, it remains in this very strong regime. And again, we were quite frustrated, but also, yeah, quite surprised by this result. So what's going on over here? You can also show this in this temperature anomaly versus AMOC strength. So this is the historical simulation. So this is the low emission scenario. This is the intermediate scenario. So this is like a tipping threshold. So there's 2.2 degrees warming. This is the tipping threshold for the higher emission scenario. And if you now plot the CO2 ramp simulation, it just goes through all those different kind of tipping thresholds. So there's no AMOC collapse going on over here. So what's going on? So we explore this in greater detail. So what I show here is the salinity differences between the last 50 milli years and the first 50 milli years. And on the left, I show you the hosing one, and on the right, I show you this climate change scenario. And when we add fresh water to the Atlantic Ocean, everything becomes fresh. So meaning that your salinity concentration is dropping, as simple as that. And on top of that, you also have the salt infection feedback as well. Therefore, it freshens even more. So you see a lot of blue, meaning it is freshening quite a lot, which shuts down your AMOC. So that is something we understand. And other places are salinifying over there. But that's under a varying freshwater flux forcing. But if you now compare that with our CO2 ramp simulation, it is actually the opposite. So only the Atlantic basin is salinifying, and regions elsewhere, they are freshening. So what climate change actually does is that it extracts fresh water from your Atlantic Ocean and it dumps it in the other basins. So it's actually like a negative hosing that you apply under climate change. So meaning that you are moving away from your satellite verification. And that's also something, if you look, for example, at the total Atlantic freshwater content, again, on the left, the hosing, and on the right, the climate change. So if these lines go up, it means that your Atlantic Ocean is getting fresher. If it's go down, it's meaning it's getting salinifying. And usually when the lines go up, that means also that your AMOC is getting more unstable. And indeed, you get the exact opposite kind of results. So it looks like from a freshwater perspective that we are actually extracting fresh water or dumping salinity into the Atlantic Ocean, stabilizing the AMOC. And you can also nicely see it for this FOVS, so this stability indicator. So this one is always decreasing and then eventually collapses. But this one is actually increasing, also meaning that the solar vector feedback is getting smaller in magnitude. So from, again, the STOML perspective, so yes, under climate change, this whole thing shifts to lower freshwater flux forcing. We thought, okay, this is happening, but this is clearly not the case. Probably due to climate change, you're also moving in that direction as well. So this relative distance between cellular verification and your initial position, they're probably moving in the same manner, such that you can get a stable AMOC state under transient climate change, if you do it slowly. If climate change is way too fast, then probably you don't have any stable regime, and that means that you do collapse it. But if you do it at a very slow pace, then you can keep up with the whole system. And finally, I'm also near, it will take 5 more minutes. Is that fine for people? Or if you're done, I can stop talking. Okay. So last thing to demonstrate is, we did this now with a slightly more sophisticated climate model. It's still a box model. It actually, I'm not going to explain tons of that, but it has like an AMOC state. It also has a idealized atmosphere. And what we actually done is we are adding like a temperature anomaly to the atmosphere. We just ramp it up linear and then keep it constant. So we ramp it up to 5 degrees warming and then keep it constant. So that means that your ocean is getting warmer. And what we've done in this experiment, so this is our control parameter. So this eta A or this EA. So we have a constant forcing, so that one is fixed. Same thing we've done before. But we also have a negative contribution. So this is our climate coupling factor, because that's not accounted for in most climate models. And what it actually does, if this box is getting warmer, you're effectively reversing the circulation again, or the hosing again. So that is like this effect between climate change and these climate coupling factors as well, like this net salinifying Atlantic under climate change. And we can actually calculate for this idealized model the verification diagram from continuation techniques. So again, you get like a shifting, so this is the reference case, you get the shifting cellular verification to lower freshwater flux forcings now. And now we can keep track of where the cellular verification is for a given temperature anomaly and also see how the system looks like. So what I show over here on the horizontal axis is the effective freshwater flux forcing. So there's this constant factor with this climate coupling factor. And here on the vertical axis, I show you the temperature anomaly. And this black dot here is, for the reference case, the position of the cellular verification. So that is over here around 0.48. That's this one as well, 0.48. And then we also, under climate change, the cellular verification shifts to lower freshwater flux forcing. So I will add next dot over here. There you go. So we have 2 dots, but we can of course calculate that for all temperature anomalies. So this is now the position of the cellular verification, and we can have actually color this in. So we have like a regime which keeps track of a stable AMOC state, but this region doesn't have any stable AMOC state, so you always go to the off state. And now we can start looking by different kind of coupling effects. So this is the case in which we don't have any coupling. So that means you just heat it up. There is no evaporation feedback. And that simply means that the on-state disappears. You're moving in this upward motion. And this is what we call then bifurcation-induced tipping, because simply the AMOC on-state disappears. Now we add some coupling effect, but do it at a very fast rate. So that's the blue curve. So you're moving in this leftward direction, so the AMOC is trying to stabilize, but it can't keep up. So you do cross cellular verification, and eventually your AMOC does collapse. you get all these curvy things. I can explain a bit during the break. And finally, we did it also at a very slow pace. And there's the green curve, and now you can nicely see that this distance between the solenoid verification remains fairly constant. So yes, the solenoid verification shifts, but you're also shifting as well. So therefore, you can keep track with you. So that's very nice, and trying to reconcile like the different AMOC perspective within the community. And finally, we can also determine the critical rate and the main takeaway from this. So we can calculate all different kind of rates. But the main takeaway from this figure is that you can always save the AMOC if this temperature coupling is strong enough or when the rate is slow enough. So to wrap up, sorry for going over time, but what I hope I demonstrated is that we have AMOC hysteresis behavior throughout the model hierarchy, all the way from STOML model to like the state-of-the-art climate models. We know that under climate change, you will get AMOC weakening, and this may trigger like an AMOC tipping event in the nearby future. However, most models don't. They have like a stable AMOC states, but this is likely due to the fact that they are in the incorrect salt convection regime. They have model biases, their AMOC is way too stable, and we think if you're in a more unstable regime, more models will show that. So the risk of AMOC tipping is likely underestimated. So the previous tipping assessment was at 4 degrees warming, while we think it's lower, around 2.5 degrees warming. But actually, we don't think that the AMOC has like a specific temperature threshold, what I also show with the CO2 rim simulations. So we think that this is more rate-induced tipping rather than by parification. And with that, I would like to end, and thank you so much for your attention.
Thank you very much, René. If you have any questions?
Yeah, I understand that fresh water comes from the poles, it melts, but at some point, everything's molten, then there's no fresh water left.
Yeah.
Is that an effect that is realistic, or?
Well, so we did the analysis. So because in the end, we always say like this additional fresh water, you could interpret that as the runoff from the green ice sheet melt that really is destabilizing the AMOC. And this effect is much smaller compared to the temperature forcing. So what we see under climate change is that temperature is pushing your AMOC down, but actually this interactive melt from that green ice sheet that is not considered because it's way too computationally expensive. So those effects are not included, but if you add that on top of that, you will get even further AMOC decline. So also our projections are underestimating this AMOC weakening by green ice sheet melt. However, this effect is very small, like only on the order of like 5% difference by 2100. So that's a second order effect. So temperature is far more dominant, and it's something we do control at the moment.
And another question, I understand the circulation from the equator to the North Pole. Why is there not a symmetric one from the equator to the South Pole?
Yeah, so with the STOML model that's very idealized, the AMOC actually stretches all the way from the southern hemisphere to the northern hemisphere. And the STOML model only describes it took like 2 boxes. So actually you need to extend it all the way from the southern hemisphere to the northern hemisphere.
But are the boxes mirror images, or is it one?
It's like one continuous going all the way from the southern hemisphere, so from the Southern Ocean, starting from around 50 south.
Sure, but why is that? Why is it not symmetric? Why is it not a mirror image on the equator?
So it has to do with the asymmetry of continents. And that there is also a lot of cooling in the northern hemisphere due to the green ice sheet. It's very cold over there, a lot of evaporation. So you can also ask the questions of why isn't there any AMOC, for example, in the Pacific Ocean?
Yeah.
And that is due to the fact that there is some preference over the Atlantic Basin compared to the Pacific Basin as well. But yes, there has been also, like in past climates, there is also some evidence of reversed circulation as well. So yeah, but then you have a complete different configuration with an open Atlantic, with an open Panama channel, for example, different width of your Pacific Basin as well. So yeah, the continental drift really also determines where you have like a preference for your overturning. Yeah.
So quickly on this, if there is an AMOC collapse, is there maybe because salinity is different everywhere for sure? Can it mean that there might be a different circulation happening in this new state that might also transport heat or transport
Well, there is always usually what we see under climate change is that the AMOC reduces to near zero values, but there is still a very shallow overturning one, but that hardly transfers any heat. Some suggest that you get like a PMOC, so Pacific Meridional Overturning Circulation, that counts for some heat, but that is not as strong as compared to the AMOC. So you also mean that things in the southern ocean are also adapting as well, because eventually the AMOC is putting some volume down, and that needs to come up somewhere else. That needs to be in balance, and so you get some completely different kind of circulation.
And other one, is a case of reversal still possible? If you would, for example, change it very fast, which is used to circulation, right? If one of the water and one of the salinity. But if you would change it very fast, so that the salinity one is the one that is dominant, is it ever say the possibility if you would change climates very fast, for example?
Like backward,
Yeah, backward, because that was the first.
Yeah, so usually when the AMOC collapses, you get a lot of freshwater accumulation, and in the equation of state, salinity is a factor 4 stronger than temperature and nullity for the same unit if you compare it to 1 unit difference. And so you need to cool it like in a very drastic way, but on top of that you also have sea ice effects. If you cool the climate again, the sea ice also prevents an AMOC recovery, or it limits an AMOC recovery. So it will be very problematic to revive the AMOC. So if it is shutting down, it will probably shut down for a couple of centuries.
I was just wondering why you see this net salinification under climate change. What is the main?
Yeah, so there are 2 important effects. So the Atlantic basin is already a net evaporative basin, meaning that the background state is already dumping fresh water from the Atlantic into the Pacific. So that's already the initial state.
Okay.
And this atmospheric bridge is getting more amplified due to the Clausius-Capron relation.
Right.
So more heating, more water vapor, more getting dumped into the Pacific basin. So there's one effect. Second effect, didn't explain that here due to time reasons, and I'm already over that, is that also sea ice is retreating poleward. And sea ice is also like its net effect, of course, when you refreeze and melt, or when you freeze it and melt it, of course, salinity remains null. But there are some seasonality differences as well. And due to that sea ice forms, you get brine rejection because sea ice is less saline. And this sea ice drifts into the North Atlantic Ocean and then melts there during boreal summer. So there is also net freshwater input into the Atlantic Ocean due to from sea ice that forms at the poles and drifts into the Atlantic Ocean. So that also contributes to like a fresher Atlantic. And if you ramp up the temperatures, sea ice retreats poleward, and this effect becomes also very small. And that also contributes to a salinifying Atlantic Ocean.
So sea ice is in these models, right? And
Yeah.
Okay. Yeah.
Any other questions?
Yeah, I just wanted to. So, if Greenland is only a very small part of freshwater, the freshwater forcing you put in this model is very unrealistic.
Mm-hmm.
So, in the real AMOC collapse, you mostly have temperature-driven AMOC collapse.
Yeah.
So a kind of negative housing instead of this positive housing. So it's mostly a rate-induced tipping.
Mm-hmm.
And it has been shown that rate-induced systems can have early tipping because of stochastic. I mean, there's like an interplay between stochastic effects and rate-induced effects that can make tipping happen for rates which should normally be in the safe zone. So, can you take that into account with weather variability in the model? Or
Good question. Maybe for next paper. But no, we didn't look at that. There was also do you write a paper that argued that the AMOC is already collapsing due to rate-induced effects? Right? It was also a paper 2 years ago.
I don't know which one you mean.
Yeah, they claim that the AMOC is already collapsing due to rate-induced effects.
Oh, you mean the Dima and Loma paper?
Yes, that one.
Yeah, I never understood that paper.
No, me neither. But there they argue that there is some already that the AMOC is tipping. So yes, this can certainly be the case. And we also find like we did this kind of this critical temperature trend for this ECCM model, but there you can also add stochastic noise as well. So redoing that would be maybe nice.
Yeah, I mean, that's a very nice way to look at that in a probabilistic framework.
Yeah, no, let's discuss that. Let's write a new paper. That's nothing to do.
Okay.
Any other questions?
No more questions? Well, then it's time for the So we gave you 1-3 for the right network and 1-3 for your availability. So
Yeah.
that's
You.
well,